The last form of control volume analysis that we are going to do is going to be applied to the conservation of energy. And so what we'll be looking at will be the first law of thermodynamics. And in fluid mechanics, we sometimes call the first law of thermodynamics just the energy equation. We have continuity, momentum, and energy. And this will be the last one that we'll be looking at for the control volume formulation. So what we'll begin with is the system equation. Remember, these are equations that apply to a fixed mass. And so what we will need to do is to be able to rewrite that equation in the control volume formulation that applies to mass moving through our control volume. So the first law of thermodynamics, we have heat transfer, we have work, and that is equal to the time rate of change of energy within our system. And so that's a system with fixed mass. And we can write out the energy in the system. Very much like we did earlier when we looked at continuity as well as momentum. And in this equation, you notice we have little e. That is our intensive property, and that is the intensive property for energy, and that is represented by the internal energy plus the kinetic energy plus the potential energy that we would have in our fluid, and that is total energy per unit mass. So like before, what we need to do is come up with a control volume formulation for this. Before we do that, let's take a look at our heat transfer term and our work term, and we'll have to spend a little bit of time on work. It's going to take time to solve that and relate it to the fluid mechanic properties. Heat transfer is easy, work is a little bit more laborious. Now, the convention that we are using here, if you look back at thermodynamics, any class you take in thermodynamics, quite often we say when you add heat to the system, it is viewed as being positive, and we'll do the same thing here in fluid mechanics. However, in thermodynamics, typically if the system is doing work, that is considered positive when the system does work on the surroundings. We're going to use an opposite convention in fluid mechanics, and that is it will assume that work is positive when it is done on the system. So that will be the way that we do our sign convention for fluid mechanics. Okay, so heat transfer positive when heat is added to the system, and work is positive when work is done on the system. So with that, what we're going to do, we have our basic equation, the conservation of energy. What we now need to do, we need to go through the process of relating that between a system and a control volume. And so we'll use the equation that enables us to do that relation. Okay, so that's the formulation that we have. Now in this equation, what we're going to do, we will let capital N equal energy, and eta being the intensive property, that will be energy per unit mass. So with that, what we can do, we can rewrite it with the energy term embedded for eta and N. Okay, so we have that. And the other thing that we are going to need to make an assumption about is the relationship with our work and heat transfer terms. So let's look back here. This is our basic equation. So on the left-hand side, we have this. When we looked at momentum equation, that was the force, and it was equal to mass times acceleration. Here we have heat transfer and work, and so we need to make a relationship between fixed mass and the control volume formulation. And for that, if you recall back to the derivation that we did to come up with the equation that relates the system to the control volume, we assumed that at one point in time the control volume and the system were co-located. And so with that, we can then make an assumption that relates heat transfer and work. So at time t0 through that derivation, that was Reynolds' analogy, we had a situation where the control volume and the system were coincident or co-located, and consequently what we can say is that heat transfer plus work applied to the system of fixed mass will be equal to heat transfer plus work applied to our control volume, and therefore we can then translate the equation into the control volume. And with that, what we have is this for the energy equation. So we have that. We're dealing with a scalar. Energy is a scalar. When we looked at linear momentum, remember that was a vector. So this is a little simpler. The place where we're now going to need to spend a little bit of time, however, is figuring out how to handle the work term here. This is going to require us to go through a little bit of analysis. Heat transfer is pretty straightforward. It's just heat transfer across the boundary. But work will require a little bit more work because we have fluid coming into and across the boundary. And so we need a way to be able to account for that. In thermodynamics, that is called flow work, but essentially we're going to go through the same sort of analysis. So in the next segment, what we're going to do, we're going to spend time looking at the work term and be able to come up with a formulation. And then once we have that, we'll be able to bring it all together, and we will have the control volume formulation for the energy equation. So in the next segment, we will look closer at work.